Hi, my name is Andy Harris. I made a talk a while ago that got really huge on YouTube about how to start thinking like a programmer. And one of the preposterous things that I said in that conversation was that there were only seven main ideas in programming. My theory is that regardless of what language you're using, there's only seven major ideas. And if you understand those ideas, well, then you can learn to program in any language. And that seems ridiculous, but I want to back that up with exactly what I believe those seven ideas are and how they work. So essentially, it comes down to this. Um, it's hard to learn programming. I've taught lots of people to program. I've programmed in many languages, and it seems impossible. Every language has a different syntax. Languages have different keywords to memorize. It's common for people to need to know four or five major languages at least. It seems overwhelming. There's a lot of ideas floating around about how to teach and how to learn, and a lot of misconception about how do I understand all of this. And what I'm trying to say here is it's not actually that hard. It turns out there are a main set of ideas which can be divorced from specific languages. And when you understand those ideas, learning a new language is simply about learning the implementation of those ideas. So, after programming for many years and teaching programming for almost as many, I found there really are a few main ideas. Those ideas tend to be universal to all languages, at least all formal programming languages. Something like HTML, SQL, not quite the same. Those aren't technically programming languages in this same way. Go ahead, send me the angry email. But I'm going to say traditional languages all have the same general features. And here's the great thing. You'll still need to learn a language, but you can learn the concepts in any language. And then once you understand those concepts and you can implement them in your first language, then the concepts freely translate to other languages. You're just learning, okay, I already know that there is such a thing as a while loop, and I already know pretty much how it works. I know its strengths and its limitations. Now, how do I do it in this new language? That's much easier than having to memorize. So, this talk really is the outline of every beginning programming class that I teach in any language. It's also the way that I learn a new language. It's not unusual for me to need to teach or write about a language I've never seen before. And how do I do it? By using these ideas. And typically, I can learn a new language well enough to produce something usable in a weekend because I understand these concepts. Okay, let's take a look. So here is the big overview of the big overview. The seven big ideas are this. We have variables or data, we have input and output systems, we have operations, branching, looping, functions, and aggregation. That's it. All of programming in any language comes down to these ideas. Okay, those ideas do have a lot of depth to them, and it takes me typically an entire semester to teach people exactly what all those things mean in all those languages. So don't think that you're going to be able to write code today in any language because I'm going to explain them. I'm going to explain these ideas very broadly. Because what it means to learn programming is to understand each of these ideas deeply enough that you can implement them in your first language. And that only comes through practice. So you still have to practice, you still have to write code, you still have to do exercises that use each of these. But these are the main ideas, and this is roughly the order that I always teach them in. And I also believe this. If you really want to learn programming, not only do you have to understand, say, variables and data in your first language, and how that works in your first language, you have to write a program that does that, that works with variables and data, and nothing else. And then you must do that before you start dealing with the next thing. Okay, I own this, I can write a program that does it. Now let's talk about input and output. You could argue we could change the order a little bit, especially early on. But okay, now let's think about what it means to do input and output, because that is dependent on variables. You know, what do you output? Often the contents of a variable. What do you input? Well, you put whatever you get from the user into a variable. And so you need to write a program that does that. And then operations and so on. So each of these ideas, my recommendation is you do a very simple exercise that just tests that idea and the things above it. And as you continue to do that, then you will find yourself able to write code in whatever language you're trying to do. And that is the art of programming. Okay, so we'll look at each of the variables or each of these ideas, and I'll sort of explain what I am talking about. Now, notice I'm not talking about any particular language. We're just talking about the big ideas. Later on, I may implement all of these concepts in particular languages so you can see how they work in Python or C++ or whatever. But a variable, the key idea of all programming. Programming is about data, and data typically goes in variables. So a data has certain characteristics, regardless of the language. It has a name. The name of variables, super important. So one of the most important things you learn in programming is how to name things so that you'll be able to figure out what they mean later. It's usually one word. It's usually best if it's not a single letter long. It's just a name. So that's one idea. Another important idea is that a variable is meant to hold a particular type of data. In your refrigerator, you have pitchers. They're for holding liquid. You have Tupperware for holding different stuff like leftovers, right? It would be bad to put your leftover spaghetti in the pitcher, right? It's a wrong kind of container. So in computer memory, everything is ultimately binary. So variables have to have data types to help them understand, okay, how do I convert whatever this is, the text or the numbers or whatever, into binary? And so every time you have a variable, you're going to be thinking about a name. You're going to be thinking about its type. Now, some languages make you be really, really specific about the type. Java, I'm talking to you. Some languages like Python and JavaScript are pretty loosey-goosey. When you just name a variable or you assign a value to a variable, it says, oh, okay, I know what type it's supposed to be. But regardless of that, regardless of whether the language tends to be really strict about you deciding the type, every variable has a type. Every variable somehow has a data type. And understanding that is key because a lot of the errors you run into, especially quite early on, are that things are not in the type you think they are. So that's an important idea. Okay, so the most common data types of pretty much every language is going to have some sorts of numeric variables. And in fact, two primary numeric variable types. You'll see integers, which are those numbers without the decimal point, 1, 2, 3, 4, 5, 0, -1, -2, and so on, but not 3.5, not pi. And then float, which stands for floating point real numbers. So remember, real numbers from math class, they can do 3.14, but they have a finite length. So typically we call them floats in programming. And they're stored in memory differently than integers. So they're not the same type. And then text is normally stored in a type called string. For poetic reasons that have to do with how the data is stored in memory, programmers don't call it text, we call it strings of characters or strings. And then the object type we'll get to at the very end of the discussion, but that's basically everything else. And it's a relatively recent innovation in programming, and it changed everything. So there could be many, many, many more. Some languages have hundreds of data types, but you're typically going to see the basic ones: integer, float, string. Okay, what else? A variable should always have a starting point. They don't always, but it's a good thing to think about when you create a variable. What does it start with? And then for each of these things, there's some more advanced topics. I never show beginners, but sometimes on a second pass through all of these ideas, some more advanced topics will come through. Later on, when we have functions, we'll think about scope. And later on, when we think about classes, we'll see that that allows us to create new data types. But for a beginner, I never really worry about that. You don't need to know that at first. First, you just need to be able to make variables and do something with them. Okay. After you understand variables, the next thing you need to understand is operations. And that is, what can you do to data? Right? So when you have data and memory, you want to be able to mess with it. And there's a bunch of different things you can do, and it changes based on the type of data. So numeric data types, right? What can we do on them? Well, math. Ugh, I hate math. Stop. I don't know if you hate math or not. You might not have even really met it yet. But basic arithmetic turns out to be really super, especially if you can get somebody else to do it for you. And that's what the computer is there for. So you're going to see all your basic math operations: add, subtract, multiply, divide. Modulus is my favorite underappreciated math operation. In most languages, you can do other things: squares, roots, trigonometry, maybe some really crazy stuff. You might have to bring in a library. It might be built in. But you can always do the mathy stuff to numeric data. What may not be quite so obvious is, well, if I have text data, then does it have operations? Well, sure, there's different things we can do. We can combine values, so I can take two pieces of text and scrunch them together to be one. I can search for some subtext inside. I can split text. Maybe it's a paragraph and I want to split it by lines, or I want to split it by words, or I want to find particular characters in there. I might want to iterate or walk through character by character, line by line, something like that. May want to transform. I may want to, convert one character to another whenever I see it, or I may want to change the case or something like that. And again, it's going to vary a little bit by language exactly what you can do and how. The important thing to understand now is that you can do these things. You should expect to find some way to do these operations on text. And the other sort of universal type of operation you're going to see is type conversion. And that is, okay, so we have all these types. There's going to be some way to convert from one data type to another. So if I have a text string and I want to convert it to an int, or I want to convert an int to a float, or a float to a string, there's usually going to be some sort of mechanism for converting data from any type to any other type. Exactly how that works varies from language to language, and that's one of the things you learn when you learn your new language. Here's how we do it in Java. Here's how we do it in C++. I'm not going to really worry about the advanced techniques because, again, they're advanced. But it turns out when we have classes, we can define operations, and we can redefine the built-in operations in some language. I can change what it means to add things. We're not worried about that yet. Okay, so we have variables, we have operations. The third primary thing you need to know is input and output. Because most programs don't just act on data. We need to get data from somewhere, the user, a file, the internet, and we need to put stuff somewhere, the user, file, internet, database, whatever. So these mechanisms of input and output are the next major concept that you'll find in every language. And we're going to begin with simply input and output to the console system. That is just a plain old text interface, because that's easy. Turns out that it's exactly the same sort of thing when you're working with a window program. You're just going to be using objects to manage input and output. But here's your basic idea. First, we have output. You print something out. In most languages, not all, it's the print statement. It's just called print. Sometimes it's called other things, cout, printf, whatever. But there's going to be some way of printing stuff out. Normally, the print outputs text. Well, if your data wasn't text, what does it do? Good question. Usually it converts it quietly to text. Maybe you'll have to do that yourself. Often, you'll have to think about ways to combine multiple outputs and types. So if you want to output text and then you want to include, say, the value of a variable, that's something you sometimes have to think about. In various languages, there's different approaches to this: concatenation, interpolation. Ooh, fancy words. Don't worry about the fancy words. Here's what you need to know. If I'm outputting some text and I'm outputting a number and I'm outputting another variable, I'm going to have to think about how to do that. That's all. And as you learn a new language, that's one of the things that you learn. Okay. So output's pretty easy. Input is also quite easy, because the idea of input is just this. The idea of input is, okay, I want to get some information from the user, a file, some other system. Really, it works out about the same no matter where we're getting the data from. We'll typically start again with the command line console because that's easy. And so input has some implications. See, input is quite easy. Get some information. The problem with it is that it requires you to do two things before you got input in most cases. And one of the things is you have to actually ask some sort of question. There's usually an output before an input. If I say, hey, give me the answer, come on, give me the answer, right? Come on, give me the answer. You're going to say, well, that's not fair. I should have the question first. And that's true. So most console style input, you're going to begin by having some output. You're going to say, hey, what is your name? What is the number you want me to add? What, whatever. You're going to ask some sort of question. In a GUI style system, what you'll tend to do instead is have a label that indicates what they should type in the next box. But there's some kind of output implied. The other thing that's implied whenever you do input is, okay, throw me the ball. Throw a ball at the computer. Do it, please. Okay. Bam, you hit me in the face. Because, see, here's what I should have done. Before I ask you to throw me a ball, I should get my mitt ready. I should be ready to catch it, right? And that's exactly what happens with input, is that before you do input, that implies that you're going to do two other things first. You're going to somehow indicate what the input should be, and you're going to create a variable that can hold the data you're going to get in. Oh, okay. Now, in a lot of systems, the input is going to tend to be in string format. So if you want to put it in an integer or something else, then you may have to do data conversion. But that's possible. It's something that happens in all languages. Make sense? Yeah, it makes sense. When we get to more advanced stuff, networking, databases, all that stuff is really just a form of I/O. And a lot of times it's very, very simple. So once you learn the basic ideas of input and output, you can extend it to different kinds of mechanisms. All right. So branching. Again, you could write a pretty good program with just input, output, and operations, right? You could write a Mad Lib is one of my favorite early ones, right? You bring in a bunch of things, tell me a person's name and a type of fruit and so on, and then I make a story. That's fine. Operations, you could build a pretty simple calculator. You take in two pieces of information, you add them, subtract them, multiply, divide. Those are good things for that. But branching is really the foundation of why computers seem to be able to make decisions. And why they even, we have this artificial intelligence. Oh, I'll do another video on my rant about AI. Because I think it's misunderstood by a lot of people. And that's maybe why they're afraid. I'm afraid of it because I do understand it a little bit and I think it's misused. But I'm not afraid of AI. I'm afraid of people who use it poorly. So, in any case, branching is the foundation of why computers seem to be smart. They don't make decisions, but they follow instructions based on a thing called a condition. If there is a second most important idea in programming after variables, it would be conditions. And a condition is simply some kind of true and false question. Those are our favorite on tests, right? True and false. Our chances are 50-50. Anything that can be evaluated to true or false becomes a condition. And every language I know of has this. And branching is simply this. You just say, okay, I throw out a condition, and if that condition is true, I'll do one set of instructions. So if it is raining, is it raining? That's a condition. It can be true or false. If it is raining, wear a raincoat. Okay, that's a condition. That's pretty great. So if the condition is true, you do one set of instructions. Most languages, that's the if statement. Now, a lot of times you might want to have another set of instructions if the condition is false, right? If it is raining, wear a raincoat, otherwise wear ordinary clothes, because that would be embarrassing if we didn't specify what we should wear in the other case. So otherwise, or it's often called else, allows us to take a condition and give it one set of code to do if the condition is true, and a second set of code to do if the condition is false. And in most languages, that's if and else. Different languages have different approaches to this. So You just need to know it's there. You're going to learn that. Okay. There's variations on this theme. We could do this. We could say, if it's raining, wear a raincoat. Else, if it's snowing, wear mittens. All right. Else, if it's 85 degrees, wear a bathing suit. Right? So what the else does is it allows us to set up multiple conditions. There's usually a variation of else. In most languages, it's like else if. And you'll see it change from language to language, but the idea is pretty much always there. The details may change. And what this does is it says, okay, check one condition. If that's true, do whatever. If it's not true, check the next condition, then the next one, then the next one, then the next one. Every language I know of has some version of this. All right, so that's really great. So you can stack conditions with else clauses. Okay, you can also nest conditions inside each other. So that allows you to have much more complex kinds of behavior. So if A is true, and then inside that you say if B is true, well, inside that part, that's only going to be true if B is true and A is true. Okay, so I'm a big fan of nested conditions. Some beginning programming teachers are not, but I like using else for multiple conditions, and I like using nested conditions for more complex behavior because it is relatively easy for beginners to handle this and get it right. You'll find variations of this. You'll see things like switch statements, select statements. Not every language has them because the behavior can be replicated through plain old if, else if. Eventually, you'll run into other ideas like exception handling and event response. This one's the most controversial thing I'm going to say. If statements can have and or in them, and I will consider that an advanced technique. And the reason is the terms and or have very specific mathematical meanings here. And unless you understand exactly what they mean, beginners tend to get themselves in a lot of trouble. And so I generally don't recommend beginners to use compound conditions because skillful use of else and nested if pretty much has the same behavior. So else if acts just like an or, and nested ifs act just like an and, with a few other benefits. I'm not going to worry about the details. Take one of my classes, I'll show you. But here's what I think about branching. And again, doesn't matter what language you're in. Okay, so the next main idea is loops. We're more than halfway through. I mean, we're getting to the end. And it's only been, what, 15 minutes? So loops. Loops are how computers manage repetition. Okay. And so, you know, the two things computers are famous for, right, is being able to appear to make decisions, that was branching, and being able to repeat things, and that's repetition. So loops are also typically based on conditions, but there's another really important thing. All loops are based on some sort of a control variable, and typically I call that a sentry variable. A bunch of other beginning programming teachers do. A sentry is like a guard, decides who stays, who goes, right? So all loops are based on some sentry variable. And the key to understanding any loop is to understand three things that all relate to the sentry. So every kind of loop, I don't care what kind it is gonna have three questions that are about the behavior of the loop. The first question is, how does the loop start? How does the loop end? And how does it change? And ultimately, these things are all also about the sentry variable. So a loop starts with the sentry variable being at a particular value, and it ends when the sentry variable is some different value, and somehow it must change so to get from the beginning to the end. That's the key, right? That's the key to any kind of a loop. And if you understand this before you worry about the syntax of the loop, you're going to have a big advantage, because all of the syntax of a for loop and a while loop and all these other variations are about these three things, about understanding how does the sentry begin, how does the sentry end, how do we change it so it can go from the beginning to the end. And any loop that doesn't work, And this is one of the most difficult kinds of problems for beginners to solve. It's not syntax errors. The most difficult problems are when the syntax is fine, but your program goes haywire. And one of the most common things that causes that is not understanding the way your loop is structured. And it's quite possible to build a loop that it's impossible to ever begin, or it's impossible for it to ever end, because you haven't tied these three things together correctly. And so the main thing you need to know about loops is not the syntax of the while loop. The main thing you need to know about a loop is, what's a sentry? How does it start? How does it end? How does it change? And then we can learn some syntax to make those things happen. Okay, on top of loops, really there's two main flavors you'll see in most languages. They're actually not quite as different as they seem, but they are used in different places. So the first kind of loop you'll often see is what's called a for loop. And a for loop, if we're going to be official, is called deterministic. And the main idea is this. The idea is when we build a for loop, we know how many times it's going to happen, right? I will not talk out in class 100 times, right? We could say, all right, my counter is going to start at 0. It's going to go to 100, add 1 every time. And then 100 times it's going to write, I will not talk out in class. Oh, okay. So that's the most common use of a for loop, is we know we want something to happen 100 times, 1,000 times, 10 times, I times, whatever. The sentry for a for loop is almost always an integer because they're easy to count with. So that's the most common form of a for loop. A for loop is also used very often when we're trying to go through a list of things, because we always know we start at 0 and we go until we get to the end of the list and we just do each thing. So when you have items in a list that you want to work through, or you have lines in a file, you want to look at each line and see if it contains some value. Or if you're going through every character in a text variable and trying to find out if it's a consonant or a vowel or whatever it is you're trying to do, there's going to be some way to do that, right? And most likely that's going to be some variation of a for loop. A lot of languages have some more advanced versions of for loops called for each and iterators and so on, and I'm not going to worry about that yet. The main idea is to know, okay, for loops are really useful when I know how many times something's going to happen. Either I know it directly, or I'm going through a list that has some sort of a set length. The other kind of loop, if for loops are deterministic, while loops are, you're very clever, non-deterministic. And that's more useful when you don't know the number of repetitions at the start. So that's more likely going to happen until the user inputs something, or some external event happens, two objects collide in a gaming system, or a certain amount of time passes, or really any kind of an event, anything that can be measured by a comparison, which is still a condition, right? So a while loop may happen one time, it may happen 1,000 times, we don't know. And so a while loop in that sense is a little bit more flexible. In a while loop, the sentry can be any type. Okay, technically a sentry can be any type in a for loop, but if you're using a string in a for loop, you deserve what you get. But in while loops, no, it's fine. You can use any type you want. You're still checking the same things. How does that sentry start? How does it end? How does it change? Again, I'll show you maybe an example in another video of all of this done in a particular language. But you can see the ideas make sense, right? It's still, how does it start? How does it end? How does it change? What's tricky about while loops is that the syntax of a for loop in most languages actually requires you to put those three things in. How does the sentry begin? How does it end? How does it change? But while loop syntax doesn't require that. You have to actually write it yourself as other statements in your code. And this is again why understanding the ideas are so important before you start just writing code. Because the implication is, hey, I should create a variable for my sentry. I should decide how it starts before I build the loop. I should figure out how it changes as a part of building the loop. I should figure out how it ends as part of building the loop. And inside the loop, I should guarantee that sentry can change so the loop can end. Again, I don't expect you to understand all of these ideas yet. I'm throwing a lot at you. But what I'm saying is these ideas are the core of programming in any language. And regardless of the language, these are the things you'll be thinking about. Okay, there's loops. So when we start talking about, say, loops, well, we can write just about anything. In fact, at this point, a language that can do all of these is complete. You really could solve pretty much every problem that you'd ever want to solve. And some of the earliest languages that I used, BASIC was one of my first high-level languages. This is all it had. It didn't have any of the other features I'm going to talk about. And you can do everything, although it's a little bit painful. So if you can do loops and variables and conditions and operations, branches, then you can pretty much do anything that a computer program can do. Pretty cool, huh? Yeah, that's pretty cool. But there are some other things that are pretty much in all modern languages. And the first idea, both of these ideas are about aggregation, about grouping things. So the first really interesting thing is this notion of a function. And so if I ask you what you did on summer vacation, you would probably give me a list of maybe 3 or 4 things. I mean, what did I do on my summer vacation? Well, I had a couple of long overdue parties because we couldn't meet the year before. I went on a hiking trip. I spent some time with my dad. Right. So 3 things, right? I only did 3 things all summer long. Well, I went on a hiking trip. That involved a lot of pieces, right? There was a lot of detail to I went on a hiking trip. And so by saying I went on a hiking trip, what you understand is there was a whole bunch of little details to that, right? And so a function allows you to take an entire set of instructions and put them in a bag and give it a name. And the most exciting thing about this is that ultimately allows you to create essentially new commands in your language. So how many commands are there? I don't know. You can make new ones. So a function allows you to take a bunch of instructions, give them a name, save them, and then when you say the name, you are creating a magic spell. You have now it'll follow those instructions. So it's a really powerful idea. And each function ideally is a solution to a subproblem. So this really takes us to the other key thing. I say programming is not about syntax, it's about algorithms, it's about solving problems. And then the next question is always, okay, how do I solve problems? Okay, here's the answer. You solve a hard problem by smacking it with a sledgehammer until it becomes a bunch of little problems. Then you solve all those little problems and put them back together. That's kind of a snarky answer, but it actually is the truth. That's how I've solved some huge problems. You break them down into smaller problems, and those smaller problems typically take our functions. And so I use a function to solve a little problem. Sometimes I have to break the parts of that into functions. And so each function is a solution to a smaller problem, and you can put them back together to make really complex solutions. So functions are designed in pretty interesting ways. Again, most languages have them. Pretty much all modern languages have them. Functions can take inputs, so we can pass stuff into them. They can produce output. They don't have to do either one, but they can, and that makes them very useful. So we can take inputs and we can produce output. Okay, that's good. So the variables that we make inside a function. So inside a function, it's like its own little program. And the variables we make inside a function have what's called local scope. I mentioned that way back when we talked about variables. But why that's really useful is it means that you can make variables that you only think about for a little while. And then when you're done with that function, those variables disappear into a poof of logic. And you don't have to worry about them anymore. So this is a wonderful, wonderful innovation. I could tell you horror stories of what it was like to write programs before we had functions with data scope. I have one story in particular. It's horrifying. It involves a very clever cat. When you see me, ask me about it. Okay, so in any case, that's another super neat advantage of functions that you may not need yet, but eventually you'll like it when you write really big programs. So a function that doesn't return a value is like a new instruction. and that could be useful. A function that does return a value can generate new values. So you can use a function to solve a problem. You can have it do a thing. That's a function that doesn't return a value. You can have it make a thing. That's a function that returns a value. What kind of thing can it make? Well, any kind you can have. So they're very, very powerful. When we look a second pass, maybe in an advanced class at functions, then we start talking about some really interesting ideas of functions like recursion and functions having first place status and what's called lambda functions, which are kind of anonymous functions and so on. Some really interesting things you can do. But a beginner doesn't need to be worried about these things. You see what I'm saying? So each of these things we can make a second pass and look at some more advanced ideas. But as a beginner, you can solve everything without it. The last idea is the one that wraps everything back together. It really does. So if a function allows you to aggregate instructions, what if I wanted to aggregate data? So let's say I was playing putt-putt, right? On my first hole, I get a 3. On my second hole, I get a 2. And on the third hole, 7. Right? So what's my score? 2, 3, or 7? Yes, it's all those things. What I would say is I have a score for hole 1, and a score for hole 2, and a score for hole 3. So it's all score, but I use an integer to separate them out, figure out which one is which. Right? So aggregate data allows you to combine pieces of information into a single variable, and it's super useful because, let's face it, programming today is about data. That's what people are going to pay you to do. Is they've produced huge amounts of data and they want you to be able to do stuff with it, right? So having aggregate data is huge. There's lots and lots of forms of it, and the details will take some time. And when you take a programming class, we'll talk about the differences between these various forms. Arrays, lists, dictionaries, classes are the ones that come immediately to mind. And they have distinctions which don't really mean a thing to us yet, and that's okay. I can show you, but again, that's what we do in a whole class. When you get to a more advanced structure, you'll deal with things like data structures, linked lists, trees, queues, stacks, and that sort of stuff. Databases like with SQL, that's a form of aggregate data. So this idea that we can take a lot of pieces of data and combine them into a single variable, that's incredibly, incredibly useful. And that has been one of the keys to modern software engineering, being as powerful as it is. I want to take one of those ideas and give it a little special attention. That is that last one of classes, because that takes us full circle. So classes is a special data type, and that can contain variables. So you can have a bunch of different variables of different types. And then you can also, in a class, have functions. So this is a piece of data, but it can have variables like a name, and it can have a function, which is something it can do, like say hi. And you can guarantee that when it starts, it has all of its properties, all of its variables have a particular initial value. Now, in the language of classes, we use special words for these things, but it's stuff you already know, right? If a function contains a variable, we call that now a property, or sometimes an attribute. If a class contains a variable, we call that property. If the class contains a function, we call that a method of the class. A special method that allows us to initialize things is called a constructor. Should you know this? No, there's no quiz. But as you take a programming class, these are things I guarantee you're going to learn, right? And the most exciting thing is when we build a class, we can take any number of properties, any number of methods, and a constructor, and maybe some other things, and create a new thing. And here's what's beautiful. This new complicated thing that we've created is a new data type, which takes us back to the very beginning, and that is we have data. Wow. So there's a lot. This was a lot. I get that. And some of it won't make sense until you see it applied in a particular language. I may do that in another video. But what I want you to understand at this point is that you can understand the main ideas of programming without any language at all. Isn't that amazing? At least you have some grasp of the things that you can do in any language. I'll come back in another video and I'll take the language, probably Python, maybe I'll do it in C++ or Java, or I could do it in multiple languages, and show you how all of this stuff is implemented in various languages. But don't get freaked out by memorizing those things, because when you get in a language, you'll look that stuff up. The thing you want to really understand is these core ideas. And that is, whatever language we're in, anytime we're programming, what do you need to know? Variables, input, output, operation, branching, looping, functions, aggregation. When you know these ideas, you can put them together to form algorithms. Again, algorithms don't really care what language you're in. And then those algorithms can be specific enough that you can convert them into lines of code in whatever language you're trying to do. Every algorithm, every line of every algorithm that I've ever written, and I've written some huge programs, is one of these 7 things. That's it. That's all they are. Pretty cool, right? Yeah, it's pretty cool. All right, let me know what you think. Have fun. Good luck to you.